Hello, my name is Nicola DeMarinis, and my project is on characterizing asteroids using photometric data. Now, asteroidal occultations and characterizing asteroids are important for many reasons, as firstly, they help astronomers understand the formation of terrestrial planets, which is essentially Earth and Mars. They also help astronomers provide insight on the formation of dynamical families, which are groups of asteroids in our solar system that have near identical properties. They also teach us about the origins of the solar system and the emergence of life on Earth, as asteroids are largely credited with bringing the heavy elements and water required for the emergence of life. For my project, I set off with three main objectives, the first being to observe and analyze asteroids at occult distant stars, the second being to derive a shape model of an asteroid observed occulting a star, and the last being to refine a pre-existing shape model of an asteroid. For my project, I had access to three different telescopes, an 85mm refractor, seen here at the top of the image, a 356mm telescope, seen here at the center of the image, and an 80mm solar telescope, seen here at the bottom of the image. Now, for all the asteroids that I'll be presenting on today, I used the 356mm telescope. And for recording the event, I used a Wattec 910 HXRC, seen here at the bottom left of the slide. I use this camera because of its wide range of exposures that it can capture at, making it perfect for asteroidal occultations. The program I use to control a telescope is called the SkyX, and the SkyX is a very simple program that uses a multitude of star catalogs to locate objects in the night sky. Here, I was locating asteroid 105 Artemis, seen there in the center of the image, and once I locked onto it, I simply hit slew to, and then the asteroid is tracked throughout the night sky. Once the asteroid is tracked, I can then run an exposure test and then move to observing and then analyzing the event. The first step in the analysis process is uploading the data to Pyote. Pyote then creates a flux by frame graph clearly showing the asteroidal occultation and the magnitude drop seen here in the center of this image. Now, due to very clear sky conditions, this asteroidal occultation had a very clear magnitude drop. The same was true for asteroids 2132 Zhukov and 234 Barbara, both of which had very clear sky conditions leading to very clear occultations. But for asteroid 53 Calypso and 336 Lacadia, that was not the case, as there was a lot of haze and a bright moon in the night sky, making there a lot of noise in the data. So to counter this, I had to run a normalization of data. Now, a normalization of data occurs when the reference star, depicted by the green dots, and the target star, depicted by the blue dots, are averaged out or divided out. And once the software completes that, the disappearance and reappearance regions become much more clear of that asteroidal occultation, making me then be able to record a positive event. The next step in the analysis process is uploading the data to Occult. Occult is a program that allows me to generate either a shape model or an ellipse of that asteroid, depending on how many observers there are. A minimum of 4 observers is required to generate that instantaneous shape model. And here you can see that I only had 2 observers on asteroid 105 Artemis, leading me to only be able to generate an ellipse. The same is true for asteroids 2132 Zhukov, 234 Barbara, and 53 Calypso, all of which only having the less than 4 positive observations required to generate that instantaneous shape model. So I had to generate ellipses for all of these asteroids. Also, for asteroid 336 Lacadia, there was a pre-existing shape model in the database of asteroid models from inversion techniques. So I was able to use my observation along with the observation of the other astronomers made that night, and I was able to refine that pre-existing shape model. As I mentioned before, there were some clear visual obstructions in a couple of these observations. These visual obstructions include clouds, haze, humidity, and moonlight, all of which were present in the asteroidal occultation of 1312 Vassar, seen here on the right of the slide. Now, due to a very bright moon and lots of haze in the night sky, I was unable to conduct a normalization of the data as there was just too much noise in this data. So I had to record a miss or a negative event. Also, as I mentioned before, there was a clear lack of observers for all of these events. I was unable to generate an instantaneous shape model for any of these events. In conclusion, 2 out of the 3 of the study's objectives were met. I was able to observe and analyze asteroids at occult distant stars. I was also able to refine a pre-existing shape model of an asteroid, but I was unable to derive a shape of an asteroid observed occulting a star. Overall, these findings broaden the understanding of all of these asteroids, and since the data is already uploaded to the IOTA website, and which is then backed up into the NASA database annually, astronomers can use this information to provide insight on the formation of dynamical families and terrestrial planets. Also, this information can be used to refine the asteroid's position and orbit, making the next occultation even more accurate. Here are my references. Any questions?